So welcome to this video lecture. This is for compiler design. This is for week number 10. So today we're going to talk about the code generation, the start of the code generation. So there's going to be introduction about, in general, what code generation is and different intermediate representations you may have or intermediate code that you may have. Then we're gonna slowly go into, or quickly go into how to do it in the actual project. As usual, when I start my lecture, I'm always giving some updates. One of the things I've added, you may see here that there's going to be some videos. Of course, the videos are not made yet, but as soon as they're going to be posted on YouTube, you're going to see some links here. So stay tuned for that. I actually put I started to have a list. That's my video I created yesterday. So I'm going to put also all the videos in the list here. Another thing also is that I've created a slide set for some exercises I have created, inspired by the very nice website from the University of Calgary. So I'm going to create another video that actually explains these exercises. And there's nothing very new to present, so I'm going to straight away go on to the lecture. Okay. So here we go. For the code generation, as I mentioned earlier, but I thought it's a good thing to recapitulate the situation. So you have the front end and the back end, generally speaking, in a compiler. The front end is composed of lexical analysis, syntax analysis, and then you may have some intermediate code or representation that is being generated by the compiler and driven by the parser, then which is followed by syntax analysis. And then you have the backend, which is actually where the code generation is happening. And the idea why you make a difference or separation between front end and backend is that the front end is actually machine independent. So basically, it does not depend on which machine you will eventually be generating the code. Let me bring the pointer here. Okay. So the front end is machine independent. So when you design your compiler, anything that is in the front end does not depend on which machine you actually generate the code for, or what is the target machine. And then the machine, the backend is where the actual code generation is happening. The concrete or target code is being generated. So of course, then this is machine independent. And if you make the separation between these two, then what can happen is that you have your compiler front end that you can actually reuse, and you design different front end, different backends that will generate code for each different machine you want to target. So that's a nice way to organize your compiler if you want to make it retargetable. Same thing can also happen. You can have one backend that generates code out, for example, of an intermediate representation. You have one backend that reads a tree representation and generates code out of this tree, generates code for a certain machine. Then you can actually have different front ends that are compiling different programming languages, and then you can reuse your back end, and then you can actually have the same back end that can be used to generate code for a specific machine, but generating code for different languages. So it's very useful if you want to design compilers that are more well organized and allow for more flexibility. So at this point, we finished the syntax analysis, and then we have the abstract syntax tree. And even in assignment number 3, this is kind of a little recapitulation here of what we did. So after you have generated the tree, then you have actually traversed the tree in order to generate the symbol tables and so on and so forth. After you have done that, or after you've done your parsing, then you have different options to choose from, which are synthesized here in this slide. So that's some of the possibilities, but I don't claim that this is all the possibilities, but that's some, simply put, some of the possibilities. So basically, you must have the lexical analyzer and then syntactical analyzer, your parser here, that is basically fed some tokens by your lexical analyzer. And then that's where you start to have some options. So either you can have an intermediate representation. For example, in our project, what we had as an intermediate representation is the abstract syntax tree. So that's basically what I asked you to do for as part of assignment number 2, which was about generating the syntax analyzer, that is generating the abstract syntax tree. As we had discussed during the parsing lectures, it's also possible to not have an intermediate representation, in which case you'd be doing what is called syntax-directed translation. That in this case, you would actually introduce your semantic actions inside of your parser. That can quickly lead to a very messy situation if you're compiling a kind of a complex language. That's why I chose eventually to ask the students to generate the abstract syntax tree so that the following steps are easier to be more orderly. So you have, in our case, we have the abstract syntax tree. You don't need to have an abstract syntax tree if you're using syntax-directed translation. Then you can actually, well, you must be doing your translation, because that's the objective, to generate some code out of this compiler. So that's what the semantic translation phase is doing. The objective here is to generate the code, but before you actually generate the code, you must actually check that this program that you are parsing, even though it might be syntactically valid, might actually be semantically invalid. And the point is that if the program is semantically invalid, then there's no possible translation that makes any sense for this program. So that's why you need actually to check if there is semantic errors in the program. If there's no semantic errors, then the code will eventually make sense. In our project, I strongly advise that you just do the checking and you generate the code anyway. So even if there's some semantic errors and you basically generate code that's possibly not going to be executable, or even if it by any chance it's executable, it does not going to lead to a program that makes executable sense. So basically in the code and in the project, you make the semantic checking. You still generate the code even if there's errors. The thing that's going to happen is that the code you generate is probably not going to be executable. Okay, so here's for the semantic translation. You even have some other options as you, and that's where is the end somehow of the front end. Because at this point here, when you check if the program is semantically valid, this has nothing to do with on which computer you're gonna execute this program. So eventually you step into the backend part, which is basically where you start dealing with the target machine on which you are or generating this code that's going to be executed on the target machine. So you have two different options. Then you can generate the code directly from the semantic translation, or the semantic actions that you are implementing are basically generating some code, as in this case, as the parse is being done. There are semantic actions that are triggered to do the semantic checking, and then some semantic actions are trigger to generate the code as you go in the case of syntax-directed translation. You could eventually have an intermediate phase in which the semantic actions are actually generating what's called intermediate code. Some examples of which I'm gonna give in this lecture later on. So in this case, basically, you are generating code that is some abstract code, but that is very low level. That's not necessarily very much machine dependent. And that's the objective, that you're generating something that is not yet machine dependent, so that you can actually analyze it in a more abstract way before you actually translate it to the executable code, which is very much machine dependent. So you can, independently of if you're using syntax-directed translation or if you're using an intermediate representation, you can or not rely on intermediate code. Normally, you rely on intermediate code if you want to do some optimization. In this course, we don't deal with optimization. It is a very important part of compilation, but we don't touch this. It's actually could be the topic of an entire course. Okay, so we have different options. So all of these options are based or have a common denominator, if you want. They're all based on the syntactic analysis. So the syntactic analyzer is the core, if you want, of the compiler. That's where it all starts, if you want. So the parser is the one that will generate the AST, and then the AST is what is going to be used by all the other phases. It's even more true if you're doing syntax-directed translation, in which case the parser is the whole driver, literally, of the whole parsing process. So you can have intermediate representations or intermediate code. As I mentioned here, intermediate representation, intermediate code. The objective of these intermediate, or one of the objectives of these intermediate representation of core code, is to be able to do some optimization. One additional advantage, I might say, of intermediate representation is that it allows you to make a separation between what happened in or at the level of the parser and the lexical analyzer, and separate it from what is happening in the remaining stages. So to basically have it divide somehow between the translation and the parsing. So this way, this module here, or the parser, is generating a tree, for example. And then once you have this tree, then you can have as many phases as you want after, which are running independently of how the parsing was actually running. That's one of the great advantages of having an intermediate representation. So you can have intermediate representation, and eventually you can have intermediate code. Mostly you have intermediate code if you want to do some optimizations. So here I'm going to talk about intermediate representation, the different kinds of different intermediate representations, and somehow also intermediate code. So at the most prevalent, I might say, intermediate representation is the abstract syntax tree. So in this case, well, again, that is a recapitulation of what we saw before when we talked about parsing. So basically, you represent the program as a tree, and each node represents the application of a rule in the grammar. So a subtree is essentially a representation of a right-hand side of one of your rules in your grammar. And then as you go, as you are using a right-hand side, this right-hand side was called by another right-hand side. So as you go, you basically are grafting subtrees together until you are generating a root node in which you are grafting all the subtrees together. And here you have the tree that represents the entire program. So that's basically what is called a parse tree, or, you know, there's the counterpart, which is the abstract syntax tree. You might say that the parse tree is a concrete syntax tree. So the nature of the parse tree is that it emphasizes the grammatical structure of the program. So it literally is a literal representation of the right-hand sides that you have in your grammar. So that includes things like parentheses, or it actually refers also to the non-terminals and the terminals in your grammar. It's actually very concrete versus it's a concrete representation of your grammatical definition. However, many of the elements that you have in a parse tree or concrete syntax tree are not necessary for doing the translation. So normally what you do is you get rid of these unnecessary things which refer to the elements of your grammar, and you want to essentially represent the structure of the program. So that would be basically an abstract syntax tree. So the idea of an abstract syntax tree is that actually it emphasizes on the computational aspects that need to be performed, or the notion of a scope and so on. So these are all effectively represented in an abstract syntax tree, and that's all that you need to know in order to do the further analysis and the eventual translation of this program into executable code. Depending on what kind of parsing method that you are using, or what kind of grammar that you have, the parse tree and the abstract syntax tree can actually range from being very similar to actually very different. As we saw, when you want to implement a LL parser, you have to remove some of the characteristics of your initial grammar. For example, you have left recursion, you have to remove left recursions. Then it adds more rules to your grammar, with that has a tendency to kind of deform your grammar by making it much more complicated and harder to understand, humanly speaking. So all this to say, if you're using an LL parser, you have to apply a lot of transformations to your grammar. Your grammar gets longer and deformed. So that's basically has the effect that there is, if you're using LL parsing, there's going to be a lot of difference between your concrete syntax tree and your abstract syntax tree. If you're using an LR method, it's likely that you don't have to apply that many transformations. So the parse tree is going to be more resembling the actual abstract syntax tree. So that's an example of a parse tree versus an abstract syntax tree. So basically here you have the same statement. So you see that in the parse tree, you actually have the presence of the punctuation and the non-terminals that you had in your grammar. All of these are actually not necessary. All that is necessary is basically to have the operators and the operands and so on and so forth. So basically these two trees are representing exactly the same statement. However, undoubtedly this one is much more simple and to the point, so that when you want to eventually analyze the nature of this statement here or generate the code of this statement, it makes it much more easy job with less clutter, I might say, in the tree. So that was it for abstract syntax trees. What is actually used in real life is more directed acyclic graphs, or DAGs. So they are somehow like a tree. However, they are a graph that actually has some restrictions. So a tree is a kind of graph, in fact, in which you have some restrictions. So that directed acyclic graph is kind of a hybrid, if you might say, between a tree and a general graph. It has many of the restrictions that a tree has, but it does not have all the restrictions of a tree. So for example, for a directed cyclic graph, it is a graph where the edges between nodes is unidirectional, such as, for example, in a tree, you have unidirectional, all the edges between your nodes must be unidirectional. And as the name says it, there should not be cycles in a directed acyclic graph, meaning that there should not be a path when you traverse the graph. There should not ever be a possibility for you to come back to twice to the same node. And there's a present, as is for a tree, there's a presence of a root node. So there's only one way you can actually enter the graph. If you would have a general graph, then you can possibly enter by any different node. That's not the case for directed acyclic graph. So why is it useful? Because, for example, it allows you to, if you have, for example, that's just one of the examples, if you have two, well, actually, that's the next slide. If you have two, if you're representing here this statement which we saw before, then you see that these two subtrees here are actually exactly the same. So if you would end up by generating the code for each of these, then you would have two pieces of code that are doing exactly the same thing. So if you want to optimize this tree, then what you can do is to actually have these, the two operands of the plus actually pointing to the same subtree, leading to have something like this, which is, of course, not a tree. So it's actually a directed acyclic graph. So that's one of the things among many others that the directed acyclic graph would allow you to do. And that's basically why they are more used in abstract syntax trees. Of course, that makes them somehow more complex to build, but the advantage is that it allows for much more possibilities, including optimization. Another kind of intermediate representation, or in this case, it's either can be thought of intermediate representation or intermediate code, because the nature of it is that it can actually be executed, can be used for execution. So what is postfix notation? So it has different names, reverse Polish notation, or Polish postfix notation, or postfix notation. So why is it called Polish? Because it would actually, it was invented by a logician named Lukasiewicz in 1924. So that's basically a mathematical notation that allows you to represent an entire expression and the operands of an expression and the operators of an expression. It's basically allowing you to represent a tree as a linear representation. So then this linear representation can actually be used by a mechanism to actually execute this linear representation of the tree. So one of the things is that it goes away with, you might say, artifices that will that allow you to structure a certain expression, such as, for example, parentheses. So it basically is somehow encoding the precedence of the expression as originally intended. I'm going to give an example in the following slide. Historically speaking, it's very interesting because it was used in the design of the ALGOL language, of the implementation of the ALGOL language in the 1960s. ALGOL, again, I'll repeat, ALGOL is one of the most historically significant programming languages in a history of all programming languages. It's one of those languages where people will figuring out how to design good programming languages and how to implement them. This language was invented as people were inventing parsing theories, designing compilers as we know them now. So, and basically ALGOL was designed in such a way that it's literally the ancestor of almost all programming languages that we know, or procedural programming languages as we know them now. Okay, so it was basically postfix notation was used for the design of the algol language to actually implement the execution of expressions. So whenever there would be an expression in a algol program, then it would be translated somehow in a postfix notation, and there would be some kind of mechanism at runtime that would execute the expressions using the Polish notation, as I will explain in a slide, in the next slide, actually. So the postfix notation can be generated from bottom-up parse. So as you are traversing the tree, you can actually very easily generate the postfix notation, which can then, as I said before, be used. It's basically a linear representation of the tree that you are currently parsing. And then this linear representation can be fed to some kind of engine that would execute this part of the program. Okay, so it does not even, it applies to some other kinds of operations. And that's actually some kind of an advantage and a disadvantage. The thing is that you cannot represent all of the entirety of a program using postfix notation. Postfix notation can only be representing parts of the program which relate to operators, which have operands and so on. So for example, if you're defining a variable declaration or a class declaration, I guess it could be possible to represent it using postfix notation, but that would be stretching it. So you can very easily represent expressions, as I mentioned earlier, using postfix notation. So if you have A plus B, so you basically have AB plus. So basically you represent the operands before the operator. So of course, then the idea is that you can use a stack operation to compute the result of this expression, which is represented using postfix notation. Then if you have A plus B times C, if you have the currently understood precedence between the operators, then you would have A, B, C star plus. Basically, the two operands of the star are B and C, then the star is applied, which is then replaced by the result, and then you would have A and the result, which are the two operands of the plus. So I guess you see how it goes. You can also represent things like an if statement. So you can understand the if statement as being an operator that has three operands. So in which case, if you have if A then B L C, then you would have ABC question mark, which is representing this if operator. So you could even represent an embedded if statement in such a way here. You could also represent or introduce in your postfix notation the notion of the assignment operator. So you see that there are a lot of things which mostly relate to expressions and statements that can be represented using the postfix notation. So here we go with with an example. So for example, if I have this kind of complex expression here, then I can actually translate it into this postfix notation representation. So the idea here is that you could use this, after you have the postfix notation, you can use this algorithm somehow to interpret this or to execute this Polish notation representation of this expression here, this arithmetic expression. So how it goes is that basically, these are each token of the postfix notation representation. If you actually see something which is an operator, then you actually pop two things from, it's basically using a stack. So it will be pushing things on the stack. So basically it's going to take some of the tokens and going to push them on the stack. And when it sees an operator, then it's going to assume that the operands of this operator are already on the stack. It's going to retrieve them, apply the operator, figure out the result, and then push the result onto the stack. So you see, oops. So you see basically what it does is that as it encounters an operand, then it basically pushes it on the stack. So what is in red is what is the elements of the stack. The last element here is the top of the stack. So for example, in this case here, the top of the stack is 1, then you have 1, 2, 9 on successively down the bottom of the stack. And then you have the element of the postfix notation, which is on the next one is in bold black. So that's the one that is currently going to be processed. So if you see an operand that is on top of the stack, the next token in input, then you basically push it on top of the stack. So 15 here was the next token, you remove it and push it on top of the stack. Then you see 7, you remove it, push it on top of the stack. You see 1, remove it, push it on the stack. 1, remove it, push it on the stack. Here you see an operator. So here basically this example is assuming that all the operators are binary operators. Because of course, if you have operators which are not necessarily binary, then you have to know what's the arity of the operator to figure out how many things you will pop from the stack in order to compute the result of the application of this operator. Here, the assumption is that all operators are binary. Okay. So when you see plus, you retrieve its 2 operands from the stack. So basically, you implement 1 plus 1. Then that gives you the result 2, which you then push onto the stack. So you see plus, you retrieve, you pop the 2 operands of plus from the stack, then you compute the result, then you take this result and you push it onto the stack. And then you go, I'm not going to go into all the steps here, but, and then you have 2 on top of the stack and 7, which are the 2 operands of this minus operator, which is next in the postfix notation representation. So basically you do 7 minus 2, you find 5. So you pop the 7 and the 2, then you push the result, which is 5 on top of the stack. And so on and so forth. Okay, and then eventually you find that the result of the computation of this expression is actually 5. So you see that if you combine the generation of the postfix notation out of a tree representation of an expression, so then you can use an algorithm like this at runtime to actually execute the postfix notation representation of an expression. And that's actually what was done in the implementation of some of the versions of the algol language. Okay. Okay, well, what's the advantage of that is that, as we will see later, one of the things you have to do when you compute an expression is you need to come up with some intermediate results. So for example, this 2 that you found here, which is the result of adding these 2 1s here, is actually an intermediate result that you need to store in order to compute 7 minus the result of this, which is 2. So you somehow, when you execute this, you need to store this intermediate result in the computer's memory. And eventually what's happening is that for, if you compute this entire expression here, then you need to have 1, 2, 3, 4, 5, 6, 7, I believe, sub-results, intermediate results. So if you statically compile the tree and then you figure out how many intermediate results I need to compute this tree, then you come to the conclusion that you need to have 7 memory cells to actually, you need to allocate 7 memory cells to store each of these 7 intermediate results. Which is can be potentially a lot of memory that is going to be consumed by your execution of this piece of code. However, as you may see, when you execute it in this way, never do you have to store each of the 7 intermediate results at any given time. So you basically are optimizing the memory consumption as you are executing this, using this method of execution. That's actually one of the reasons why they actually used that for algol. Back in the day, computers did not have that much memory, so they had to optimize, to use optimization techniques like this to execute the programs using as less memory as possible. Okay, so that's it for postfix notation. So you see that's not necessarily something that would be used in compilers nowadays, or maybe some variation of this would be used in terms of optimization. But in a way, that's why I included it, because I find that this is an interesting discussion topic in terms of having an intermediate representation that can actually be used for some execution mechanism. Okay, so going more into the area of intermediate code, then what you can have is what is called 3 address code. But here we're going into intermediate, not intermediate, so this was talking about, yeah, I'm going to go back to the slide here. Sorry for the switching of slides. So the abstract syntax tree, the parse tree, the DAGs, and so on, these were intermediate representations. You could say somehow that the Polish notation is some kind of intermediate representation, but it's actually some kind of hybrid between intermediate code and intermediate representation. However, in the following slides I'm going to present, this is going to be literally pure intermediate code. Okay, so here we go on 3 address code, which is some kind of intermediate code that you can generate. So that's essentially 3 address code is in intermediate language. So it is a very low level language that you use to actually represent in an abstract way the actual execution of the program. So you might say this is some kind of assembly pseudocode. Of course, assembly language is very highly machine dependent. When you use an abstract representation or an abstract language, you don't want to, the idea is that you don't want it to be machine dependent. So that's why it's kind of assembly pseudocode. It looks very much like assembly code, but it's not an actual assembly code that is linked to a particular machine. The idea is that then you can, once you have this representation in this assembly pseudocode, it becomes very easy to actually translate it into actual assembly language or machine language. So it does that, it breaks the program into short, uniform statements requiring no more than 3 variables. But basically, that's why it's called 3 address code. If you remember your assembly language, most of the assembly instructions that you write would have essentially 3 operands. For example, you might have a mult assembly instruction that's going to take 2 values, for example, from 2 registers, compute the result, and then put it into another register. Hence, you have 3 operands to this. This kind of instruction. So it is basically an intermediate or abstract language that is using addresses However, here we're not talking about computer addresses. You're basically talking about, for 3 address code, it's more abstract. So basically you're talking about some kind of variables that you use to represent the computation. It doesn't use, for example, this notion of register that assembly language would be using. Rather, it uses variables, abstract notion of variables. So this allows 3AC or 3 address code to be more abstract than assembly language. So it allows you to more easily design some kind of algorithms that would analyze them and analyze 3 address code and optimize 3 address code. So you could have several different compilers for different language that are generating all the same kind of 3 address code. Then you could have an optimizer that can run on this kind of 3 address code, independently from what program is being compiled originally. So having an intermediate representation, one of the objectives is to be able to design algorithms that operate on this abstract representation independently of where it came from, or eventually where it's going to go. Okay, so here's some examples of 3 address codes. So for example, if you have x equal to a plus b times c, then clearly you see here that you have to multiply b times c and then apply the operation. I'm going to go on board for the first time. So let me share this so that we can see better. So you have basically x is equal to plus a times b c. So basically that's what we're talking about here. So essentially here you have t, which is equal to b times c. So as you are parsing this or traversing the tree here, then you see that what's happening is that you start having some temporary results that are represented, that are storing the values of an entire subtree. That's going to be a recurring theme in this lecture. This notion that a certain subtree is represented by a temporary result. And then eventually you have T1 here, and then you have T2, T1. Anyway, A plus T1. And then eventually you are taking T1, T2, and you are putting into X. Okay, so let's go back to the slide. Okay, so essentially here you have T is B plus C and X is A plus T. So you see here that literally I'm using 3 addresses or 3 aliases to addresses, or you might say 3 variables. Each of these separate instructions, or you might say micro statements or instructions, consist of at most 3 operands, or using at most 3 operands. So you can even translate something more complex that you may recognize here. So you have B times B goes into T1, and then 4 times A goes into T2, and then T2 is multiplied by C, goes into T3, and you subtract T3 from T1, put it into T4. So you see you start having all these temporary variables that you need to use somehow to compute the final result, which you then copy into the variable X. So this is essentially a lower level, much more lower level representation of this higher level expression that you represented. You represented this higher level expression in terms of lower level sub-expressions. or sequence of execution of sub-expressions. And you see also that in this case, it's basically you compute something and then you put the result somewhere else. Okay. Of course, in terms of assembly language, what you do is you take values somewhere. Either these are literal values, or you actually retrieve a value either from a register or from an address somewhere in the computer's memory. You take these two values, you apply this operator, and then you put this result somewhere else, normally either in a register or into another memory cell. Okay, so that's how eventually many, I would say, assembly instructions are organized. And you see that this is very high level, and this is much more resembling assembly instructions, even though it's an abstract representation of assembly instructions. You could even translate a for loop using three-address code. So you see that's what's happening here. First, before you enter, you initialize T0 to 0. Why am I using T0? Maybe it should be I, but anyway. So you initialize this counter here to 0. Then you have here some hookups here that you can actually branch upon. So here you have this go to instruction that makes you go to L1, which is this label here that you have assigned to this statement. Of course, the assumption here is that all of this is executed sequentially. Okay, so that's basically a procedural, exactly like most of the computers that we are using are doing a procedural execution. Okay. Okay. So you basically translate the statement that you have inside of the for loop in terms of this here. First thing you do, initialize this value to 0. Then you check if the condition is true. And if this condition is if the condition is false, then you would actually branch outside of the loop. If it is true, then you execute this, and then you branch back, re-evaluate the condition, and so on and so forth until the condition is false, in which you go out. You see that even for more elaborated statements, such as a for loop, you can actually generate three-address code. We will actually see many of these kind of patterns of translation in the next lecture, where I will show you for each of the different syntactical constructs of the language in the project, what it corresponds to in terms of a pattern of assembly expressions, assembly instructions. Okay, so as you saw, this notion of temporary results here, all of these are temporary results. Okay, but this notion of temporary result is very important, central to the code generation phase. So these temporary variables are generated at compile time. Well, they could actually, as we saw with the Polish notation execution, you could actually have some kind of engine that would, dynamically create them using a stack. But that's certainly not what we're going to do in the project. If you want to optimize things, maybe you're going to rely on something like this. In the project, we're basically going to assume that for any of the temporary results, you're going to reserve a memory cell to actually store this temporary result. It's not very optimized, but it actually works. So in the generated code, the variables will eventually refer to actual memory cells. So for example, if you have the three-address code as this one here, this will eventually, when you want to execute this three-address code, it's going to have to be translated into actual assembly language instructions of this form here, which are themselves, for example, 3 refers to register number 3. Okay, So eventually you're going to have to abide with the syntax and execution mode of your assembly instructions. So depending on what assembly language you are generating code for, you're going to have to translate that into some of the assembly language instructions. So that's it for 3-address code. Another very much related abstract language that you can use to represent executable code is quadruples. So basically you have 3-address code that is represented like this. Eventually you can actually represent this using quadruples. It's called quadruples because there's an operator and then there's 3 operands. So you see that it's very, very much resembling 3-address code, and it is also very much more compared to 3-address code. Quadruples look very much more assembly code. So quadruples is kind of in between in terms of abstract representation. It's in between 3-address code and assembly code. Okay, that's it for that. Another thing that is very much used nowadays is what's called an intermediate language. So you have, for example, when you are compiling your Java program, it will eventually generate what is called bytecode. Bytecode is a computer language, which is some kind of abstract representation of the code that's going to eventually be executed. And this abstract representation, the bytecode, is actually executed or interpreted by the Java virtual machine. So just like when I was explaining how the reverse Polish notation can be executed by an algorithm, the same thing can be said about the bytecode. Bytecode is some kind of encoded representation of your Java program into this bytecode language. And then you have this Java virtual machine that will take the bytecode and somehow execute it. Okay. So that's what is notion of an intermediate language. So your Java compiler, it actually translates your Java program into another program, which is a bytecode program, which can then be executed by the Java virtual machine, which is itself a program, which is an interpreter that you use to actually execute your Java program, or the bytecode representation of your Java program. So if you want to rely on an intermediate language, then of course you need to implement this virtual machine, which is going to be executing programs that are written in this intermediate language. So of course, then the advantage of that is that you can compile this virtual machine onto different computers. And then that suddenly makes it so that any program that you feed this virtual machine can then be executed in any computer on which you have compiled the virtual machine. That's an absolutely great advantage for this model of execution. It makes programs much more portable. So that's one of the things that made Java have a booming popularity, because it allowed to have this portability. Also made it so that it became initially to be a very good language for internet computing, or computing over the internet, using browsers and so on and so forth. Okay, so well, Java is under bytecode and the JVM. That's just one example. There are many other languages like Perl or PHP or Python or Ruby. There's many other languages. These are probably the more popular ones. But there's many others that are actually using exactly the same model of execution, and they have their own intermediate language. But even some people that are maybe just for fun, translating a C++ program into bytecode, and so that you can then execute a C++ program on the Java virtual machine. There's all kinds of possibilities. As soon as you have this interpreter that has their own language, then anybody can take whatever language and translate it into bytecode, which can then be executed using the Java virtual machine. But virtual machine is very flexible kind of tool. And that's exactly what we're going to have in the project. If I can go here to the website here. So what we're going to use in the project is the Moon machine. So if you go here, you have the code for the Moon machine. Moon machine was designed by one of our profs that's now retired, Peter Gorgono. Hi, Peter, if you ever see that. So you see that we're still using your marvelous piece of machinery here. If you go in the source here, you see that there's a C program. They basically can compile this using your Visual Studio or your GCC. Visual Studio might give you some warnings and so on. So as far as I understand, don't worry about them. If you have some errors though, that's something I would not be aware of. So maybe you can talk with the tutor about if you have some problems to compile it, which I doubt you would, then please see the tutor. So basically this Moon program is an interpreter that is going to, whose objective is to execute programs written in the Moon language. So the Moon language is, or the language of the Moon processor. So you're gonna basically generate code in this language, and then you're gonna compile the Moon machine, and you're gonna feed this code to the Moon machine, and the Moon machine is gonna execute. Moon processor is gonna execute your target code. So your code, the code you generate is not gonna be written into assembly code of your machine. It's gonna be written in assembly code for the Moon machine. So in a way, the Moon machine is like a JVM, if you will, except that it doesn't execute bytecode; it executes Moon machine code. So here is a part of the lecture where we're going to go much more in details of the project. So here, this is a representation of where we are in the project and how it's going to go. So we did lexical analysis, generated a token stream, then did a parser, which generated an AST, abstract syntax tree. So that was assignment number 2. This was assignment number 1. Assignment number 3 basically took the AST and essentially generated what is called a decorated abstract syntax tree, where what's decorating and thing is that as you are, for example, you were generating the symbol tables, you were basically going over the tree and were generating some, for example, symbol tables and making the connections between the symbol tables, which represent different scopes in the program. And as you came lower in the tree, you came onto variable declarations, which were then associated with a certain node in your tree, or a certain subtree, variable declaration subtree, which was a child of, for example, a function definition. So this subtree was actually representing an entry in the symbol table, and this is basically a decoration that you added to your abstract syntax tree for this particular node. The variable declaration node was decorated with the actual symbol table entry that it actually represents, that this entire subtree represents. So you're decorating the tree by associating aggregated information that represents the entire subtree. And eventually, all of these variable declarations were children of a function definition, and the function definition had an entire symbol table that represents its own scope, in which the children variable declarations, which contain the entries of the symbol table, were actually gotten from the function definition node on top, and basically gathered all the symbol table entries from its children variable declarations, and then put them into the symbol table. The symbol table is also a decoration, in this case, of the function definition node and subtree. So you're basically adding or aggregating information and putting them in the nodes, depending on what kind of node they are. So that's what's meaning by abstract syntax tree decoration. Then eventually what you're going to do is that you're going to take this decorated tree that contains symbol table entries and type information and whatnot that you needed to create and use in your semantic checking in assignment number 3. And then eventually you're going to take this decorated abstract syntax tree, you're going to retraverse it again, and then you're going to generate some code. Do some more semantic checking, and then eventually generate some code. The code that you're going to generate is basically going to be Moon code that you actually feed to the Moon processor. That's basically what's going to be your assignment number 4 here. You're going to retraverse, possibly multiple times, the decorated abstract syntax tree, and you're going to generate the code. As you traverse the tree, you're going to sequentially, as you traverse this tree in a particular order, you're going to generate sequentially the code, the Moon code that corresponds to the executable code of this tree representation of your program. Okay, that's, yeah, okay, so this is how you should organize things. I've already explained the visitor pattern. I can't tell you how much I propose to you, advocate to you that you use the visitor pattern. Not that you have to use the visitor pattern, but it makes your life so much easier after you have figured out how it works. It's a little bit of gymnastics to figure out how it works. In terms of patterns, that's probably one of the most complicated to understand with the, in terms of, you know, the mechanism that's involved and all the different steps and so on. It's a little bit complicated to understand, but once you understand it and you have implemented it, it becomes so much easier to actually implement your semantic actions, figure out where your semantic actions should go. It actually does also the traversal very easily, enables you to do the traversal very easily. So I can't emphasize enough how implementing the visitor pattern is an extremely good investment that pays off eventually. So eventually what you have to do is your semantic verification and translation is done using semantic actions. So you already had to implement semantic actions to generate the tree, and eventually to, when you traverse the tree in assignment number 3, you're using semantic actions that you trigger, you know, depending on where you are in the tree, you trigger some semantic actions depending on what kind of nodes you are currently in, and so on and so forth. No matter what model you use, visitor pattern or not, that's the same concept. Traverse the tree, depending on what node, what type of node you are now, there should be some semantic actions that are associated with this type of node, which you fire as you, either as you come into the node or as you resolve the entire subtree of this node. Okay. So yeah, as the tree is being traversed, semantic actions should be automatically triggered. So there are eventually dozens. In industrial compiler, there would be hundreds of semantic actions. So if you want to do all the different kinds of processing that are necessary for the symbol table generation, type checking, translation, there's eventually dozens or hundreds of semantic actions that you have to create. Then you have to very carefully associate them with specific node. What's making more complicated is that some semantic actions require that other semantic actions have been performed before. For example, if you are generating the code, the code generation needs to have the semantic, the symbol tables. So all these semantic actions that are generating the symbol tables need to all happen before you trigger the semantic actions for the code generation. So basically it says that you need to have to group your semantic actions into phases, so that you create a group of semantic actions that are executed before any other group of semantic actions. So you need to create groups of semantic actions and then figure out what group is depending on the other group, and that you trigger them in the right order. So if you do this like free for all, it's going to be a very daunting experience. So essentially, you could create a semantic action module, and then you organize them into sub-modules for each of the different phases. So that's what you would need to do if you're not using a visitor pattern. However, if you are using the visitor pattern, all of these problems you have to solve are all managed somehow very easily by the structure and operation of the visitor pattern. So the grouping into phases, the automatic triggering of the semantic actions, all of this is kind of magically managed by the visitor pattern. It's like the visitor pattern was created for that. It was not, but it's actually an excellent example of a very good application of a design pattern. So, okay, so this is how it's going. So basically you have your abstract syntax tree. If I can show you the code. So that's basically my module here that's implementing all my abstract syntax tree nodes. So that's, for example, my node class here. That's a, for example, variable declaration. That's my variable declaration node, so on and so forth. So that's basically my AST module here, which is, of course, used by my different visitors. If you remember, you basically create your abstract visitor. Where's the visitor in the code? The code, oh, by the way, I didn't re-mention that again. This code I'm talking about here is this. If you open this zip file here, contains a bunch of Java files organized into an Eclipse project. If you put that in Eclipse, then you'll get what I'm talking about here. So this is my abstract syntax tree module. Then I have my visitor module here, and here I have my visitor class, which is the one I'm referring to here, abstract visitor class. That's the class I'm actually referring to here. Then if I can go here, then I have a semantic analyzer module, code generator module, and then here I have concrete visitors, a set of concrete visitors that are actually representing different phases. So each of these red boxes are a phase. So for example, when you do semantic analysis, there might be different phases. Like in assignment number 3, you did the generation of the symbol tables. Then once you have the symbol tables generated, then you can actually do some semantic checking, like for example, type checking. Type checking requires that you have the symbol tables already defined. So naturally you would define a visitor for symbol table creation and then a visitor for type checking. That's eventually what I have in the code. I have a visitor for symbol table creation, or a module for symbol table creation, and I have 2 concrete visitors, one for computing the symbol tables. This other one here I'm gonna come back to later in this lecture. And then I have my semantic checking module, which contains only one concrete visitor, which is for the type checking. And eventually, as you see, I have my code generation visitor or module that contains two different visitors, as I will explain also later. So all this to say that you can, eventually what you want to do is to create one concrete visitor, which is essentially a subclass of the abstract visitor class. And then essentially you have your, what you do is you, essentially what's happening is that you implement your semantic actions inside of the concrete visitor. And then when you fire it, it's actually is executing as the tree is being traversed. It will fire in the correct order somehow your semantic actions that you have put inside of the visitor. I'm not giving all the details here because I've explained that in a previous lecture, I think 2 lectures before this one. Okay, so you can have, if you need to have different phases, then you implement a different concrete visitor for each of the phases. Does not need to be different phases. For example, in the code here, for the code, I have 2 different concrete visitors here. That does not mean that they are to be executed one after the other or sequentially. Here I basically have 2 different ways of generating code. So as we'll see later, you can use a tags-based code that you can generate or stack-based code that you can generate. Here I basically created 2 different visitors. If you use one, it's going to use tag-based execution. If you use the other, it's going to use it's going to generate code for stack-based generation. So, okay. But the point is that these 2 are 2 entirely separate ways, different ways to generate code. So I've created 2 visitors which are separate from one another that can generate code in a different way, and they don't interact with one another or depend on one another. If you're generating different phases, then they might actually depend. For example, that what is done by the code generation phase visitor, the symbol table generation phase visitor will do some processing, which is necessary to have happen before the semantic checking phase visitor. So that's how, if you use the visitor pattern, which I again strongly advocate that you do, that's how you would end up structuring your project. Okay, so here I'm going to go in much more details about how to implement these semantic actions for the code generation. So in general, semantic actions are about giving a meaning to the compiled program. In particular, when you generate code, you essentially have a program that is expressed in a higher level programming language, and then you want to give a meaning to this higher level programming language in terms of a lower level programming language that is being executed by the actual computer. So as we said in the first lecture, so the idea is that a human wants to have higher level abstraction mechanisms which are implemented in a higher level programming language. However, the computer does not know about this higher level programming language, so you need to somehow instruct the computer to translate these higher level concepts into lower level concepts that it can understand. Okay, so it's about giving meaning to this higher level programming language concepts in terms of concepts that are understood by the very low level computer. So again, in general, when you have semantic actions, you have 2 counterparts, semantic checking and semantic translation. Because it's possible that when you have your AST, if you have a correct AST representation of a program that is syntactically correct, it's possible that the program is semantically incorrect. So that's why you have to, as you're doing the traversal of the tree to do the translation, you have to also most often check if the program can be correct. You could, as I said earlier, as I hinted at earlier, you could still generate the code for a program that is semantically incorrect, but it would most likely lead to a program that you cannot execute, or if by any fluke it could be executable, it actually would not make sense in terms of what was your original intent. You know, that's actually what is very difficult when you when you compile your, for example, your C++ program. It compiles successfully, and then you execute the program, and then something wrong happens, which sometimes is very hard to understand. It's just that your program was syntactically correct, might even be semantically correct, but then there was a flaw in your program, which is very often hard to figure out. Okay. So in most cases, the semantic checking is, or semantic translation is conditional to the semantic checking. In the project, I advocate that you still continue, even if there's semantic error, you continue generating the code. Okay. It's just that the code is most likely not going to be executable. Another thing is that there's no such thing as a code generation error. So there's lexical errors, parsing errors, or semantic errors. There's no such thing as a code generation error. So you don't have to make error detection or error reporting or error recovery for code generation. It just does not exist. So what are all the semantic actions? So there, essentially, you have semantic actions that are associated with the different syntactical constructs of your language. So literally, as you're traversing the tree, as you come to the root of a certain subtree, this node represents actually a certain syntactical construct that its subtree is actually representing. So any such syntactical construct, for example, include declarations such as variable declaration, type declaration, or class declarations, function declarations. You also have subtrees for control structures such as an if statement, for or while statement, function calls. And then you have also assignments and expressions, assignment operations, as we saw earlier. Some examples, arithmetic expressions or logical expressions. These are all syntactical constructs. And for each of these, you will actually have semantic actions that will have to be created to actually generate translation in terms of moon code or target code for each of these building blocks of the language. What's eventually going to happen is that for each of the different nodes, you're going to create a semantic action that generates code for this particular syntactical construct. And it's going to be basically like a mini pattern of code generation that you are going to trigger every time you come onto a certain node. Much of these, I will give some examples today, but much of this will be explained in the next lecture. It's important to understand that what I was pointing out here as the syntactical building blocks of the language is applied to manifestly typed programming, procedural programming languages. If you would have functional programming, or I don't know, any other paradigm that is not procedural and manifestly typed, then you would have different kinds of syntactical building blocks. Okay, so here I'm going to give very, I might say, detailed description on how to process different things in terms of how you generate code for a specific syntactical element as I have pointed out here in this list. So first we're going to see how you can generate code for processing declarations, such as, for example, a variable declaration, or eventually a function declaration, or a class declaration. So essentially, when you define a declaration, you are defining a semantic element of the program. So either you're declaring a variable that is being used by the execution of the program, or you're defining a function. For example, you have a function declaration that, yes, declares some variables that are being used internally to this function, but also contains somehow some statements that are going to then be executed. So basically, declarations are either a container or an atomic element that is contained in a container. Okay, so what you do as semantic checking as you're processing declarations. So the only semantic checking when you see declarations is to ensure that every identifier is declared once and only once in the same scope. That's something that you actually did in your assignment number 3. So as you come into a function declaration node, a function definition node, then this actually defines a scope, and this function is part of a high level scope. So you have to make sure that whatever the scope you are in, if you are referring to a certain ID, that this ID is valid inside of the scope, and that as you declare something in a scope, that it is actually part of the higher level scope to which it belongs. That's what you do when you construct a symbol table. That was already done in assignment number 3, which is the symbol table construction process. So as you encounter declarations, then you either create create symbol table entries, as well as the symbol tables which you populate with symbol table entries that you have encountered as children of a higher level declaration. Okay, so this is essentially something that we did in assignment number 3. So that's just basically a recapitulation of the context here. Okay, so that was for the semantic checking, which is mostly done by the symbol table construction process. However, eventually you encounter things such as statements which refer to the variables that were declared, in which case you have to check in the symbol table. Anytime you refer to a variable in an expression, for example, you have to check if this variable name is declared in the scope in which you currently are by looking up in the symbol table. So how do you do then, after you did the check, how do you do the translation? So very important concept is that anytime you refer to something, either for example, a variable that is being declared or an entire scope, you have to define what is the size of this thing, because eventually you're going to compute some values. So you define a variable A, which is an integer, then you will need to store a value in this variable A. So you're going to need to somehow associate this concept of your variable A with some memory cells in your computer. So you're going to have to define how many memory cells do I need to reserve to store the value of my variable A. So that, of course, depends on its type. So if it's a basic type such as integer or float, that's a fixed size. However, if you define arrays or if you define classes, then you need to define what is the total size of the array, or if you define a class, and what is the size of a value that is of a certain type, which corresponds to a certain class. We'll come back to that in more details later. So memory allocation, this is basically what we're talking about. Eventually, when you generate the code, you have to do some kind of memory allocation. In the project, we're going to only do static memory allocation. The most complex that we may go is using a stack. We're not going to use heap allocated variables of any such kind. This is very nice to have. You actually must have this if you're designing a language that is worth using. However, of course, it makes it much more complicated to implement. So we don't have all the time in the world in this course, so we're not going to have dynamic memory allocation. The most complicated thing that we may have, which I will not even force you to do, is to use a stack operated mode of execution. For example, when you call functions, that you use a stack frames and so on. I'm going to explain next week how to achieve that, or next week, next lecture, how you achieve that. So yeah, we're talking about memory allocation. So as soon as we talk memory allocation, you have to know how much memory you should allocate for everything that you encounter in processing. You want to store values, compute values, you need to store these values. So what is the size of these values? So basically the first step is to figure out for each of the identifiers that I define, what is the size of memory do I need to reserve in order to store a value for a variable, or if I'm calling a function, how much memory do I need to actually execute this function, which is, of course, the total size of all the variables that are defined in this scope. Essentially, what I have to do is to go over my symbol tables and then figure out what is the size of each of the elements that I have inside of a scope. And if I total them, then it's going to give me the size of each of the scopes that I've actually defined, be it a function or a class. Okay, so eventually there's going to be two different modes. So as I've shown earlier, for example, here you have stack-based code generation and tags-based code generation. So these are two different ways that you can, that I'm proposing to you that you use. And that's what I'm actually referring to here, and I will very often refer to that. In this particular lecture, the explanations are based upon tags-based. So basically here, what you're going to do is you're going to allocate memory to a certain variable, and then you're going to define a label or a tag that is going to be used inside of the Moon machine code. If you're using the offset, then you're not going to have tags, rather you're going to compute offsets. So you're going to refer to a certain address number, and then if you're storing, for example, an object, then this object is going to be stored in a lot of consecutive memory cells. So if you want to refer to an object, you're going to refer to the top address of this object. If you want to refer to a certain member of the object, you're going to compute what is the offset of this particular member with regards to the top address of this object. So of course, in real life, the offset is actually what is being used. The label execution model, it's not something you would see in real life. However, again, this is something that may work for simple cases. If you don't want to do offsets, there's going to be some grading elements that are going to be related to whether or not you can compute offsets and execute using an offset method, but there's also going to be some partial marks if you're doing label execution, label mode of execution. One of the things is, for example, if you want to use recursion, then you actually must use an offset mode where you're using an execution stack and so on and so forth, and stack frames for your function calls. So in this lecture, I'm going to concentrate on the label mode of execution or tags base of execution. And in the next lecture, I'm going to concentrate more on the stack-based execution. Okay, so here we're going to concentrate more onto how do you process variable declarations. So here, if you for semantic checking, if you encounter a variable declaration, then you actually verify, you make sure that this variable has been properly entered into the symbol table. And then for the translation, if you're using the label execution mode, then you have to generate a label for this variable. You might think, here I'm going to rely to the board, you might think that this label is equal to the name of the variable, but just going to give you a very simple example here to show how this is not generally the case. So if you have a program like you have this function f1, takes some parameter, returns an int, and then you have, let's say, a variable a defined here, and then let's say you have another function, returns a float, and then you might have also, or let's make it float, also named a. So you might say, okay, I'm going to use the variable name in order to generate my tag names. It's important to understand that your tags are going to be part of the same Moon program. So that you should not have two different tags with the same name, because that's going to be an illegal program. So essentially, you cannot use the variable name as the tag name. So eventually what you can do is, because you have a variable a here, variable a being defined here, even though they're not the same scope, the Moon program is not going to know about this notion of scope. So there should be different tags generated for this variable a and this variable a. An easy thing that you can do is to, let's say, there's a tag for this variable and this tag for this variable. They're both named a, but you may actually put the function name or the scope name before the function name, the variable name. So that the tag for this variable is f1a, and the tag for this variable is f2a. Okay. Same thing would apply also if you are defining classes. So all this to say that you have to take care of the fact that maybe some variables are duplicated across different scopes. And you must somehow have a label generator that's going to generate unique names. Okay, so in this case, you would be generating label names. If you are using the offset mode of execution, then you have to figure out what is the offset. Eventually, no matter if it's the offset you're talking about, you are using, or the label, eventually you have to store this information, either the label or the offset, inside of the symbol. You have to insert this inside the symbol table or in the node itself, which would be another way to decorate the tree. Okay, so depending on if you're using the label execution or offset execution, you have to either generate labels, calculate the offsets, and store that somewhere. But eventually, as you generate the code, you're going to be using this information. So again, this information can be put in the abstract syntax tree node, but if we go to inside of my abstract syntax tree, the root node is, or the superclass of node is node. So all my nodes here are subclasses of, my specific nodes here are subclasses of my node class. As you see here, I've added a lot of different variables inside, or containers inside of my node. And each of these, for example, These are my original things that I can store in a node, but as I was actually generating new visitors, for example, when I designed the type checking visitor, I had to include this type here. So that, for example, if I want to do the type checking of an expression, then I need to know the type of every sub expression. So that means that every node that is a children of an expression node, every step of the way needs to know what is the type of the sub expression that it represents if I want to be able to do the overall type checking of my entire expression. So in doing so, I had to introduce that here into my node class. So you see that this is a very kind of local need I had for a particular visitor, and I've introduced one more variable inside of my node class. If I start having dozens of visitors and I'm creating dozens and dozens of variables, then my node class is going to become very, very cluttered and possibly not so easy to understand anymore. So you have to be careful when you do something like this. Maybe some information would be better to store it in the symbol table rather than in the node. Of course, the symbol table is stored in the node, but at least it groups things together instead of having a huge number of variables defined in the same class. Okay, so eventually what you need to do is to compute the moon labels, to generate moon labels, unique moon labels. So you will have to create a certain function that generates moon labels, either by aggregating like this or by sequential generation of labels. Whatever you want, you need to have a unique moon label generator. And eventually what you're going to have to do also is to have some kind of visitor that is going to go over the table, the symbol table structure, and then compute what is the size of every element of a table, and eventually what's the size of an entire table that represents an entire scope. That is actually what is done by my visitor compute memory size visitor here. Basically, it goes over the tree, and then whenever it sees a table, then it loops over the elements of the table and determines the size of each of the elements, as well as the size of the entire scope or table. Okay. Okay, so if you use the label mode of execution, then many of your moon assembly instructions are going to refer to labels. If you're using the stack mode of operation, then which basically you're going to refer, instead of referring to a label associated with a certain memory cell, you're going to use the address, directly the address of this memory cell, possibly using an offset. So you're going to refer to the starting address of a certain composite variable, such as an object. You're going to know what is the starting address of this object. You're going to also know what is the offset of a certain member inside of this object with regards to the starting address of this object. That's what I mean here by stack frame plus offset. Stack frames and so on, we're going to cover that next week in the next lecture. So here's an example. First of all, it's very important to understand that this program here doesn't make any sense. Like there's functions defined here that are not even called. These variables are not declared. Doesn't matter. That's not the point of this example. Point of this example here is that there are things that are declared in every scope. And then, for example, there are variables that are being declared in the program function. There are variables that are being declared in func2 and func1. So if you generate the symbol table for this program, it's going to generate something like this. What I want you to understand or see here is that anything that is a var here in my, well, first of all, you don't have to do it exactly as I did. I'm just giving you an idea of what needs to be done. So every table should contain an element. For example, a function contains variables that are declared inside of the scope of this function. And here you have the name of this variable, you have the type of this variable, and here you start having what is the size of every of these things that are being declared. So basically here it's assumed that an integer is 4 bytes. So for example, int235 is an array of 2 by 3 by 5 of integers, which are each of them 4 bytes. That's basically summing up to 120 bytes. Okay, so basically I need to compute what's the size of every of the elements. And then eventually I sum up, I do a running sum of each of these, and that gives me the actual offset. Why is it minus? Because basically I'm gonna set up in the execution model I have in my particular program, I'm gonna have my stack frame that is pointing here. And then if I have my stack frame for my function, so basically my stack frame is here, and then I'm gonna go down, and the elements that are stored in the stack frame are stored in contiguous memory going down in this stack. That's why these numbers are negative. You could do the inverse, but that's what I chose to do in my implementation. And then eventually have this offset, the entire offset of the entire function 1 scope. Because eventually function 1 could actually be calling another function, in which case the stack frame will be put on top. So then you need to actually increase the pointer, the stack pointer by the size of function 1, so that you're now pointing to the first element, the first memory cell that is storing the new function that you are now calling. That's basically saying that you need to have a running sum of all the elements. And then once you come at the end, that gives you the total size of this element that you're talking about, being it a function or a class. This example does not have a class, but this is the same concept. Okay, another thing that I have in this example is, you see I have my temp var here. Eventually, as you are processing these expressions here, you figure out that this expression is composed of sub-expressions. Anytime, as I've shown you in the previously on the board, anytime you come to a sub-expression, there needs to be a sub-result that will be storing the value of this sub-expression. Anytime you come to such a node, you basically should have semantic action that is triggered that will add a new temporary variable inside of this scope. Okay. It's not necessarily how it would be done. It can be optimized, as I hinted at when I explained how to, execute the Polish notation. So you could actually optimize that. This way of executing and compiling would be quite wasteful of resources, but again, that works. So one of the objectives of the project is that you actually are able to execute your programs, and that would achieve this goal. So anytime you come up onto sub-results, you should have a semantic action that will generate an entry in the symbol table for this sub-result, figure out what's the type of this sub-result, then from the type you determine what's the size of this sub-result. Then you do, again, the running sum at the end. So you see that the semantic actions for adding the temporary variables should all happen before you actually do the running sum at the end. Okay. Okay, so this is a much more detailed here of what you would do in terms of code for your semantic action for a variable declaration node. So that would be inside of the project here. This is for the code generation, tags-based generation. That was for what? Variable declaration. So variable declaration, I go here, var declaration. So that's essentially my visit method here. That's essentially my semantic action here. So for this visitor, for the tags-based code generation visitor, when I visit a node of type var declaration node, then I trigger this semantic action. So what it does is that it generates this moon code here. This is essentially a string that I construct that is a string that is actually moon code. So I basically accumulate this moon code into a string, and eventually at the end, I would output it into a file. Okay, let's go back to here. So this is basically my semantic action for code generation. We will see later in the next lecture, much more details about what is the moon code, what does it mean. This is basically here showing you the first glimpse of how to generate moon code. All this to say that here I had, for example, in a program in a certain scope, I have 3 variables that are being declared. Eventually, as I traverse the tree that's generated by that, I'm going to come into variable declaration node, and then it's going to basically retrieve what is the type, what is the name of this variable, and whether it has some dimensions, if it was an array. In this case, it does not. So it knows that the size of an int, so if the type is, which is my child number 0, is the type is int, then I actually generate this code here. So you see that my visitor here is extremely simplistic. It only generates code for things that are int and does not generate code for arrays or anything other than that. It only generates code for a atomic integer variable. Okay. If you encounter something which is not atomic, in fact, if it encounters something which is an array, it's going to think that this is an atomic int. Okay. So all this to say that my code is very simplistic. Okay. You should not expect that it actually does the whole thing. Okay. I didn't want people to basically copy my code. I don't mean either you should proceed in exactly the same way. I'm just basically showing you how you could implement a visitor pattern and how you can implement, giving you some simple example of how you can implement semantic actions for translation. So if you have a tree that contains, that is a representation of this portion of a program, this visitor would actually generate this code here. So you see that what it does, these are of course, these are comments in your moon code. This is a moon instruction that will reserve 4 bytes. So essentially here, you have a label which you can refer to using other moon instructions. So you can refer to, essentially A is an alias for the memory cell in which you have started to reserve 4 bytes. Okay. Okay, so yeah, maybe I can explain this in more detail here. Let me stop share here. So essentially you would have your program, your memory, computer's memory here. And let's say every word, let's say, is 4 bytes. Or let's say every word, it's not the case, but let's say every word is 2 bytes. Okay. So then you would have A, and then B, and then C. So essentially A in your moon program is an alias for this memory cell here. So if you refer to A, you actually refer to this memory cell here. Okay. So if you go A res, I don't know, 400, then it's going to be something like this. A, and then you have a lot of memory cells here, and A actually represents this address here, which is the address of the first memory cell that you have reserved for. Share. Okay, here we go back. So essentially here you have A and B and C, and you reserved 4 bytes for A, 4 bytes for B, and 4 bytes for C. So you basically here allocated memory for A, B, and C. So what happens, so this is for atomic variables. Here you have an atomic int. What if you have an array of int, or what if you have objects? Arrays and objects are basically composite data types that are containing atomic data types. So the idea is whatever you do, in our case, as I mentioned earlier, we only have things which are of fixed size. The size of everything is going to be determined at compile time. Nothing is going to change size as we go. So it basically means that as we don't have pointers or dynamic memory allocation or a heap, makes things much more simple, but of course much more restricted. Also assumes that, again, as I said, everything is of fixed size. Okay. That's why we actually define array dimensions, which actually need to be constants. For those of you who have wondered in most programming languages why your arrays, if you declare an array, like say in C++, an array that is not a pointer, that's actually why your array sizes need to be constant expressions, because it requires that size be determined at compile time and that it's not going to change. Okay. As I mentioned earlier, the addressing should be stored in the symbol table, as I exemplified here. Here, the addressing that is being stored is offsets. Okay. If you would be using labels, then you would actually store labels into the symbol table. So if you're using label execution, you store labels in the table. If you're using offset computation, then you store offsets in the table. That's a little bit more complicated than that, because if you are, okay, let's go do another example. Because once you start using objects, things get a little bit more hairy. Let's say you have class A, and you have a variable A, and so you have class B, and then you have also variable A, okay? So again, you could say, okay, I'm gonna say, okay, let's say you're using labels. So you're gonna say, this is my variable A of my class B. And you might say, this is variable A of my class A. So apparently this is solving the problem, but it is not if, for example, you may have in your main function of your program, you may go and define 2 variables of type A, named A1 and A2. If you do so, then suddenly what you start having is that this variable A1 and variable A2 both have a member named A, and if you use this aliasing, basically, you start having these 2 variables would actually refer to the same moon label, okay? So that actually doesn't work. Even if you think it might work, if you start having 2 variables in the same program, which are declared that are of the same type, what you actually need for this to work, you need to have offsets. So you need to be able to refer to each of the different members of a class by using offsets. So you can refer, for example, if you have the computer's memory for this program, you can refer to this as the moon tag A1, for example. You can refer to it as main A1, and this is main A2 as a tag label. So this would actually be main A1, which would contain the object A1. And then you would have main A2, which is this label associated with this memory cell here that contains, it's the first memory cell that refers to this object A2. But then you see that you here, if you would have this label here, then that would imply that I have the label AA, and here again, label AA. So I cannot have two labels which have the same name. So that's why if you're allowing your program, which you should, if you allow your program to have more than one variables defined of the same type, not only in the same scope, but in the entire program, then you actually need to use offsets in order to refer to the elements of a class, of an object. Let's go here. Okay, all this to say that yes, you can use labels, but if you want to use objects, you need to do the offset computation. So it's not that simple. Anyway, there's going to be some, in the grading scheme. If you are using offsets, but not for objects, then you're going to have partial marks for that. So I'm going to make it sure that, you can do, you can execute, for example, you can say, I can execute programs, for example, that have only a main function that define variables which are not that are not objects, that, for example, that are only of atomic types. And then you're going to have a subset of the marks for that particular achievement. Then you're going to have more marks if you can use objects, more marks if you can use arrays, more marks if you can have arrays of objects, and so on. So this is how it's going to proceed. So if every achievement, every step of the way, you're going to get marks as you achieve more. Okay, so one of the composite data types that you have available is arrays. So here the assumption is, as for many programming languages, for example, like C or C++, it basically assumes that an array is stored in a contiguous number of memory cells. Okay, so for example, if you declare this array A34, then it's basically this first memory cell here is storing A00, and then the first row is being stored contiguously here, and then it goes to the second row, and then to the third row. That's how you have an array of 3 by 4. Okay. Then if you know what is the size of the atomic type of the array, and you know what is the size, number of rows and the number of columns, then you can use some kind of formula like this to compute automatically what is the offset. So if you know what is the starting address of this array, and you know all of these informations that I mentioned, then you can use this expression to compute the offset at runtime. Okay. So the point is that if you want to store an array, to store any of these arrays here, you need to compute what is their total size in order to reserve enough memory cell for this array to be stored. And eventually, as you're going to refer to each of these elements, you're going to use this formula to figure out what offset to use to actually refer to an element inside of the array. So as I hinted at by example here, you can also have objects that are being declared. For example, here in my program here, I have an object of type A that is being declared. The thing is that the type A is declared here. It's inheriting from B, and it also contains an element which is of type C. So essentially, when I declare an object of type A, it has all the members of A, all the members of B, and it has a member C, which means that if this A contains a C, then it also needs to reserve memory for all the members of C. So all this to say, if you reserve memory for an A, you need to reserve memory for a B as well as a C. So in terms of your computer's memory consumption, basically when you reserve an A, you're gonna maybe refer to A as a label, but then you're gonna need to compute what is the offset. You're gonna figure out in what order you store each of these elements, and then how you actually refer to each of the elements by their offset versus in what order you decided to store them. So first and foremost, when you want to reserve the entire block of memory, you need to know what is the total size of all these elements here, which are contained of something of in something of type A. Now, let's go to expressions and assignment statements. So that was for literally variable declarations I just explained. Let's go to expressions. So as I hinted at 2 or 3 times by now in this lecture, when you compute an expression, then the nature of an expression is that it's composed of sub-expressions. And of course, an assignment statement refers to an expression, okay? So it's basically running around the notion that you have sub-expressions, and each of these sub-expressions, you should determine what's the type of the sub-expression so that you can figure out what's the type of the entire expression. Eventually, also, for each of the sub-expressions, you need to store a temporary value for each of the sub-expressions. And so that means you need to create temporary variables, as I explained before. So that eventually, if you have a program like this, and you have A is equals A plus B times C, then you have B times C needs to be stored in a temporary value. A plus the result of B times C, it's stored in another value. And also when you do A plus 6, it needs to be stored in another temporary value. So as you traverse the tree, eventually you're gonna have to create a semantic action that introduce these temporary variables inside of your symbol table. Eventually also as you do this type checking, as you were doing in assignment number 3, you have to check if the typing of the entire expression is correct. Eventually, you're gonna generate code. And so it's gonna actually be generating the code sequentially. As you do a depth first search traversal of your tree, in this order of the depth first search order, it's going to sequentially generate the code as the depth first search is being done. So, for example, here, as you are traversing this tree, you go here, and then here, and then here, and then here, yet you complete this entire subtree here. So eventually, you're going to compute the B first, and then you're gonna output this code here. And then as you compute the C, then you're gonna generate this code here. As you come back here and you complete this subtree, you're gonna generate the code for the multiplication. And then you're gonna put the result of this multiplication into a temporary variable. So this is load words, it's basically loading the value at address B with offset 0. Basically, R0 is, as I will explain later, the assumption is R0 always contains 0, because offset 0 is very often used. So that's the assumption I have in my whole code. Okay, so I load the value of B in register 1, load the value of C in register 2, then I multiply the value contained in R1 by the value contained in R2, and I put it into register 3, which is the code I generate when I come back here. And then I take the value stored in R3 and put it into the memory cell that corresponds to the label T1 plus offset 0. So you see here that I have generated, as I traverse this subtree here, sequentially I have generated this code. All the code generation is going to happen like this. As you traverse the tree, you're going to sequentially generate code. And then the same thing happens as I actually resolve this whole entire tree here. And the last thing I do is I take the value stored in R1, which is the temporary result that is here, and I actually store it into my variable A plus offset 0. So what's important here is to understand is that as you traverse the tree, you're going to have to create some semantic actions that are going to generate Moon code like this as you go. Okay. So that's one example. So for example, the multop node, which is this node here. So if you look at the code I'm generating here, this is basically the code I have here. Okay. So if you look at this semantic action that I have here, that's basically load word, multiplication, store word. That's basically what I have here. Okay, so that's mini pattern of code generation that I execute as I'm here, as I'm processing this here. This is what I have inside of my semantic action here. Okay. Okay, this is, I'm gonna open a parenthesis here. So you might see that there's two streams, that Moon exec code and there's Moon data code. One of the concepts, basic concepts of assembly language is that there is some memory cells that contain instructions and there is memory cells that contain data. And the thing is, if you try to execute a memory cell that contains data, most likely it's going to make the machine crash, right? Or the program stop executing. Let me stop share here. So literally your Moon code, when you load your Moon code, is going to copy your code inside each of the memory cells. And then the Moon machine is going to sequentially go over these and going to want to execute each of these. Now, the point is that if you, for example, inside of this code here, you, let's say, reserve memory for your variable A, and you put this Moon instruction here, then literally this memory cell contains data. So if the Moon machine goes and executes this sequentially, it's going to come here and you're going to try to execute this, which is data. Most likely it's going to crash. So all this to say that when you do reserve operations, you should not put them intertwine with the code. So what I do in my code here, basically I have two streams, one stream for the code and one stream for my variables. So I have one stream of Moon code where I store all, for example, my reserved word, memory cells, these are two instructions to reserve memory cells. So I basically put them all in the same block of code, and then all my instructions, which is the executable code, I put it into another stream. And eventually, the last thing I'm going to do at the end of my program, I'm going to put halt as my last instruction here. And then my program is going to be the executable code, halt, and then this block of code here. So that makes it so that my executable code can refer, for example, to A, but the program execution would stop here and never execute my data part. Okay. So that's why in my code, I have moon executable code and moon data code. Executable is the instructions, and I'm sorry, I should have, so that's why I have moon executable code and moon data code. And then I append these two at the end of the processing. That prevents the machine from trying to execute my data code. Why do I do this like this? Because you have to understand that here I'm sequentially generating the code for the execution. But at this point also I need to reserve memory for my temporary result. So sequentially, that's the order of things I do, but that does not necessarily mean that's the order in which they should be put inside the code, the sequential code. Okay, two things here. So here you see that this code is using registers. So here in my simple code, I've actually used what I call a register pool. It's basically a stack of strings. So it's strings, what is it? If I go to my code here, okay, here. So here I actually create my register pool. What is my register pool? It's basically a stack of string that contains a string R12 to R1, okay? It does not include R0 because by convention, I always assume that R0 contains 0, so I should not be using R0. So I use register 12 or 1 to 12, I put them in the stack, and then when I want to use a register, I pop it one register from the stack, use the register, and when I'm finished using this register, I push it back on the stack. So it's basically a register, very simple register allocation scheme, because you have a limited number of registers, so you want to use them in orderly manner. Another thing is that for the variable names, in my very simple implementation, I'm using the variable name as the same thing as the moon tag name. Okay. So if I refer to some variables in my programs, I assume that these are the labels I'm using in the program, in the moon code. Basically, it does not work if I have two things of the same name defined in my program. Of course, that's a limitation that you should overcome if you want to do more complete implementation of the compiler. Yeah, my code has a very important limitations. It's basically there just to give you a simple example. That's for the assignment statement node. So if we look at the code here, the assignment statement is the last thing that's being processed here. So it has load word, store word. So if you look at this code here, it basically has load word, store word. Okay, it uses a register. So you see that my register, I know here that I have to use local register. So for example, in my code here, I need to use I need to use a register to take T2 and store it in a register and then take this value and put it into A. So I need a register to make this transition, right? So in my code here, I hard-coded R1, but it's possible that R1 is already taken and I'm going to use something else. So that's why you need to use a register allocation scheme, which I use a very simple one in my code, which actually works. So before I start this code generation, I get a register from my register pool, basically pop the next available register from my pool. I use it here, and as soon as I finish this code generation, I push it back because I don't need this register anymore. So I make it available for some other code when I'll generate other code later. sequentially. So you need to implement a solution for your register allocation, as I just explained, and you need to have a Moon tag name generation. In my case, I generate Moon tag names for my temporary variables, but my code does not take care of what I was explaining earlier on the board. If you're using objects, basically the code generation for objects in my code does not work. Okay, if you want to use objects, you actually must use offsets. Actually, my code does not work either if I have two variables with the same name in the entire program. As I explained earlier, you can partially solve this problem by appending a variable name with the name of the scope in which it appears, especially for variables that are defined or declared inside of a function. So we're coming to the conclusion that was actually a lecture that's somehow longer than the lectures I'm used to do. I guess it doesn't matter in our case here, since we don't have class time restrictions. Well, I'm not going to go over all of this in all the details. Already discussed that. Just simply say that so most compilers would use an intermediate representation because it allows for optimizations. It allows to make a separation between the parsing and the following phases. It allows you to have many more consecutive phases because if you do a syntax-directed translation, very difficult to have, or not very difficult, but it's harder to actually have several phases. So intermediate representations, very, very useful feature to have in a compiler. Most or all compilers would actually have that. So in the project, we're using Moon code. So I would invite you to, as soon as possible, compile the Moon machine in whatever compiler you are used to use for C programs. There's some documentation. You may want to look at that. I'm going to try to be, as you saw, I gave some explanations today. So for everything that I use for the code generation, I'm going to somehow explain it. However, you have to go to the tutorial or office hours, online office hours, if you want to figure out how to use the Moon machine, which is a command line tool. So you can, for example, trigger it in trace mode. If your program does not execute, you can see what is stored in the memory of the machine and so on. So there's different things that are possible and that you need to know if you want to use it properly. And I cannot stress enough that using the visitor pattern, this can be done without the visitor pattern, but it is much, much easier to do with the visitor pattern. So you might think, and I don't like the visitor pattern, it's complex to understand. However, the time you will spend to understand how the visitor pattern works and to put it in place is going to be very minor compared to the time you'll spend later on if you actually don't use it. Okay, so it's a good investment of your time if you are not using it yet. So these are some references. Yeah, so that's it for the lecture number 10. So I'm going to create soon in the days to come some resources, some video for week 11. I'm also going to create a video for the exercise slides I talked about earlier. And yeah, see you around. Bye-bye.